Let's solve a harder optimization problem. This is a type of problem that you will probably see on your AP exam, your midterm, or your calculus final exam in college, because it starts with a word problem and you have to build your own equation from it. This is very, very common. So let's begin. A farmer has 1,200 feet of fencing and wants to build a rectangular pen along a straight river. The river forms one side of the rectangle, so no need fencing there. What dimensions will maximize the area of the pen? So, as always, let's start by drawing a picture. So we have our beautiful river. This is why I'm not an artist, guys. But we have the river and we have a rectangular fence where the river acts as one side. So, step one, let's define our variables. All right. So we're gonna say let x be the width of the pen. So let's say the side perpendicular to the river. So we're gonna say that is your x, that is your x, and then we're gonna have y be the length of the pen or the side parallel to the river, like that. All right. Step two. Now let's write out the constraints that we have. So I'm gonna just call this constraint. So since the river makes one side of the pen, we only need fencing for three sides, so two widths and one length. So the fencing equation then becomes just the perimeter, right? So perimeter of rectangle is just 2x plus 2y is equal to p. And p we want to maximize, right? So maximize this. And the farmer has 1,200 feet of fencing. So we're going to say the maximum perimeter we can have is 1,200. And we only need two x's and one y. So we don't actually need this 2 right here. So this becomes 2x plus y. And that is our equation. We're going to call that the constraint equation. So I'm going to write that in blue. Constraint equation. All right, now on to step three, what we are actually solving for, the area. We're trying to maximize the area. So let's write an equation for the area. So step three, area equation. All right, so area of a rectangle is just length times width. So in this case, it'd just be x times y. But for optimizations, we need the area in terms of just one variable. Again, we don't want to solve for implicit differentiation. So we're just going to rewrite all of this in terms of one variable. So we're going to take your constraint equation and let's solve it for y. So we're going to solve it as y is equal to 1,200 minus 2x. Now let's plug this y into the area equation. I'm just going to, that comes from there. And this will go into your area. So we have area is equal to x times 1,200 minus 2x, right? So this is already maximized because we included the 1,200. And now your area is in terms of just one variable. So this is going to be 1,200x minus 2x squared. All right. So on to step four, which is now we are ready to take the derivative. So again, we have We have our area equation is equal to 1200x minus 2x squared. Take the derivative of both sides, you get dA dx. Again, this is dA taking the derivative of a over dx in with respect to x, because that is the variable that we are solving for right now. We get 1200 dx over dx. You don't have to write that. I'm just writing it in to kind of get it into your brain. Every time you take a derivative, it comes with one of these bad boys. But you don't have to write it for now. Minus, that is 4x dx over dx. All right, so now let's set all of this equal to 0. This is to solve for critical points. And whenever you set a derivative equal to 0, you find your maximums and minimums of the function. So if you had a graph, right, say we have a parabola, we solve for our zeros, that gives us the maximum and minimums of that equation. In this case, it'll give us the maximum width or length. So once we solve or equal to 0, let's solve for x. So we have 4x is equal to 1200. X is then equal to 300. So this is our width. So now that we have the width, let's try to go back and solve for our length. So we're just going to plug it back into the constraint. So step 5. Solve for y. So our constraint is 2x plus y is 1200. 2x plus y is 1200. We know x is 300, so that just makes this 600 plus y is equal to 1200. Y is equal to 600. And that is our length. And remember the units. So let's just take a moment and check. So x is 300. And y is 600. And we need two x's and one y. So two x's, which is 600. One y is 600 for a total of 1200. So that does not go over our maximum amount of fencing, so we're good there. And that is us optimizing our area, our surface area for this problem. So kind of final remarks. The key to optimization word problems is first draw a picture, make it clear what you're solving for. Define your variables, write your constraint equation, right? What is the limiting factor in this whole process? Write the quantity you want to maximize. So in this case we wanted to maximize our area. Substitute so that you only have one variable. So again, it simplifies the differentiation process. Take the derivative, set it equal to 0, find your maximum and min, get that variable, then plug that variable back into your constraint equation, solve for the second variable, and that is the full process that should work every single time for any single optimization problem. Hope that helps.